Thank you. Yeah, hello everyone. My name is Calle, as Jesper said, and I'm going to talk a little bit about software obfuscation. First, a little bit in general, what it is, why you want to do it, and then one particular way you can achieve this with the LLVM compiler framework. So first, just shortly about myself. As I said, my name is Carl or Calle, and I work as the head of security at the healthcare company Kry. And in my spare time, I play a lot of these capture the flag competitions for the team Hacking for Soju. And if you want to get in touch with me after this talk or later, you can use one of these methods. Yeah, and that's it. And I'm also going to tell you, I can tell you beforehand that this is going to be a bit of a shorter talk, but I don't think anyone will mind as we're getting towards the end of the day and people are a bit tired. But hopefully it's going to be some interesting content here. So yeah, as I said, I'm going to talk a little bit about software obfuscation, and then we're going to talk a little bit about compilers, and specifically about the LLVM compiler framework, and then how you can use this to perform software obfuscation, and how you can some techniques for testing this, and finally we can talk a little bit about what you can do to try to counter these techniques. So software obfuscation in general is just the art and science of making software more difficult for someone else to understand. This can be done at various different levels and areas of the program, and with a lot of different methods. And this also depends on what kind of programming language or execution context we're talking about. So something that you would typically find in your everyday life, which isn't maybe actually done for the sake of making it harder to understand, but for performance reasons, is that most websites minify their JavaScript code. So if you go to any popular web application and you look at the JavaScript code, you will see that everything is single character variable names and all the white spaces removed and so on. I think that's primarily done for performance reason, but a side effect of it is that it's quite difficult to understand what the code is doing. You can also do, so then this is done at kind of the source code level, because program languages like JavaScript, you write the source code and then you ship the source code. The source code is the program. But then you have other compiled languages, both mid-level languages like Java and .NET based languages, where you compile your source code into an intermediate representation, which is then interpreted by a virtual machine. And then you can make changes to this intermediate code to make it more difficult to understand. And it doesn't make as much sense to make changes to the source code, or some kinds of changes to the source code doesn't really make any sense, because it's going to be compiled into this other thing anyway. Same goes for lower level languages like C++ or Rust, or languages like those which are compiled down to machine code. Typically it doesn't make any sense to modify well, some kinds of modifications to the source code, but you want to modify the actual program so that when someone else gets this program, it's more difficult to reverse engineer it and understand what it's doing. And there are a whole bunch of different techniques for achieving this, and these are some of the like broad categories of techniques that you can find in software obfuscation. So one very interesting concept is the control flow flattening. So you can imagine that you have some program which has a structure like this diagram to the left. You can imagine, doing something, and then you have a branch where you take one of the branches depending on something, and then you do something at the end. So this can be one part of your program. And as a reverse engineer, just being able to see just this structure without even knowing what's in these colored boxes already gives information about like the general structure of the program. We know that there are two cases of something. So what you can do then is that you kind of rip this whole graph apart, and you just line all these basic blocks up next to each other. And then you have kind of like an internal counter which says which block we're going to execute next. So we execute all of this. We have a loop and like a switch statement or something. So every lap of this loop, we choose one of the blocks to execute, and then we go back to the beginning and we choose another block to execute. So now this structure has been completely destroyed, and it's very difficult to get an overview. Like, is this 5 different cases, or are we just going to execute all of these 5 in a row, or what's going on? So that's one technique. Another thing is self-modifying code, which is a fairly descriptive name. It's basically code which during execution will modify the program that is running, either modify the actual piece of code that's running, or maybe decrypt or modify other parts of the program. You can also have dead code, which is basically you insert a lot of stuff in the program that effectively does nothing. So you could imagine that every time you assign a value to a variable, you add some extra additions afterwards, but then you subtract the same amount immediately afterwards, or you divide by 2, but then you multiply by 2 again later, and you just insert these meaningless things. Or maybe you insert some stuff which will copy data from one place and then copy it back later. And yeah, all kinds of just meaningless stuff which will not affect the actual semantics of the program, but it will make it more tedious to go through and understand the code, because the program becomes larger while still containing like the same amount of information, so that the density of information in the program goes down, and makes it more tedious to analyze it. You can have, as I said, packers, which execute parts of the program in stages. So maybe you have a small part of the program which will decrypt another part of the program, and which in turn will maybe decrypt another part of the program, and so on, which makes it very difficult to know beforehand what the program does. Very related thing is droppers, very common among malware, where you will download additional code from the internet, for example. So we'll just have a small part of the code in the program, and then you dynamically retrieve code that you will execute. You can insert a lot of anti-debugging techniques in your program to make it difficult to debug the program. There are from very simple techniques which just tries to detect if you have a debugger running, and in that case it will either shut down or do something different, or modify its behavior in some way. There are other programs which abuses different features in your operating system to make it inherently hard to debug them. Maybe you will have a program that will fork itself into multiple processes, and one of the processes will start debugging the other process, and make modifications to the program while it's running, and all kinds of funky stuff, which makes it very annoying to debug a program. You can also have basically create completely new programming languages and have like a virtual machine embedded into your program, which executes this made-up programming language, which makes it very annoying because then you have to create basically new tools specifically for analysis of this program. The downside is that it can have a quite heavy performance impact depending on how you do this. So today I'm gonna talk about this, how we can do some of this obfuscation, and I'm gonna limit myself to these low-level languages. So when we write code, nowadays we typically don't write machine code instructions directly because that would be extremely boring and annoying and error prone and just horrible. So we have created higher level languages like C++ and Rust, and then we take a compiler. It becomes very cumbersome because you need like one compiler per pair of programming language and target, and this quickly becomes completely infeasible. So what modern compilers do is that they have something that looks like the top image, so including an LLVM does this as well. So what you do is you have a front end where you take this specific programming language like C++ or Go or Rust, and you transform this into an intermediate language. So it's not quite something that a computer could actually execute, and it's not quite something that the human would reasonably able to read and understand. So it's something somewhere in between. Then the compiler can do a lot of processing on this intermediate representation, and then finally we transform this intermediate representation into something that's specifically targeted towards the platform that we want to execute this code on. And the really good thing about this is that if we just create these front ends and back ends, all the tools and smart things that we come up with that operates on this intermediate representation, they are applied to all of these different combinations. So we get like all of this for free. So we make some kind of, let's say we create an optimizer which does, for example, loop unrolling. So it looks at the loops in your code and analyzes them and see if it's better to actually just split this up into just explicitly listed statement, for example. That would be one thing that an optimizer could do. And if you create this then for the LLVM framework, it will be able to do this no matter what programming language or target you are targeting. So that's really cool. And LLVM has a lot of built-in of these components in the pipeline for optimization and things like that. But you can also create your own, and other people have also created a lot of cool tools that work on this LLVM intermediate language, which gives you this benefit that you get like all of these different targets in one, like for the price of one. So as I said, LLVM has this kind of like pipeline where you have this intermediate representation, and then it goes through different stages of this pipeline where it's this intermediate code is like processed in different steps to like simplify it and optimize it and make it as good as possible. And it's fairly easy to write a simple such a component in this pipeline, a pass. You can write one fairly easily yourself. So this to the right is like a minimum example of a pass. This doesn't really do anything of interest. It just prints out a message every time for every basic block that it's executed on. So it like just lists all the basic block in your code. Not very interesting, but this is like maybe the minimum amount of code you would need to write one of these passes, and they're written in C++. I don't know if you can write them in other languages, but yeah, this is what you can do. But we are not here to optimize the code. We are here to obfuscate the code. So just as well as we can write the pass that makes the code more efficient, removes unnecessary instructions, and so on, we can make code that's more difficult to analyze. And there was this really nice blog post from Quarks Labs from a couple of years ago, where they did this, and they based this around this mathematical expression. So they would, in some places in the code, they would decide that instead of having anywhere in the code where you would need something that you want to evaluate to a false value, you could replace this by this expression. So you would take two variables in your code, x and y, and then you would just generate two random numbers, a1 and a2, which we can then insert into this expression. And you would also pick two prime numbers, so we could have a table of prime numbers. And we would replace something in the code that was just false, and we replace it with this. And if you do the math, this will always hold. So that's nice, because the program is still behaving in the exact same way. Everything that was, if this expression that we were to evaluate, it was previously always false, and it's still always going to be false. But it's not as obvious. If I would have like a snippet of code where you would say like an if statement, which would say if false, which means we never execute this piece of code, that's very obvious. We're never doing that. But if the if statement says if this, then it's not like immediately obvious whether that's true or false and in what situations. And the nice thing about this then is that, sure, we could have made these modifications in our source code when we wrote the program. But the nice thing here is that when we implement this as an LLVM pass, we kind of get it like at scale for free. So we can just, we could maybe decide on some kind of density of how often you should insert something like this, and then just like tune this up and down depending on how horrible we want the code to become. And you can, come up with all kinds of different funky expressions and transformation to your code that will not make the code behave any differently in practice, but will make it much more difficult to analyze. So I did, as a small example for myself, just one of these where I would take a value and move it around in a few different places. I copy it to a register and like push it to a stack and fetch it back, and just juggle it around a few times before using it, which will add a bunch of instructions which are completely meaningless. Oh yeah, so this is one way you can use LLVM to create obfuscation. You create these passes which you insert into the LLVM pipeline, and the nice thing is now you have created an obfuscator not only for a single language, but you have created an obfuscator for all the languages that are supported by LLVM, which is also a cool thing, because if you would have made this at the source code level, say I make the equivalent thing for C++, that would absolutely work, but it would only be for C++. Now I get all of these other things for free. Another thing you could do, which some people have done, is that they have completely forked the LLVM project. to build further obfuscation routines and tools. And the advantage of this is, of course, that you are no longer constrained to the exact interface that the LLVM provides to you. So you can do more complicated obfuscations. On the other hand, it comes with all the downside of managing a fork of like a major software project that you have. If you want to stay up to date, you have to remember, like, pull in all like upstream patches and manage that and make sure that's compatible with your code and so on. So it can be quite an endeavor. But some people have done this and they call it the Obfuscator LLVM, which is exactly what the name says. It's an open source fork of the LLVM compilation suite able to provide increased software security through code obfuscation and tamper proofing. Which brings me a little bit to, which I should have talked about earlier, but didn't, is like, why would you do this in the first place? And there are, of course, a couple of different reasons. You could, for example, a lot of, when it comes to like DRM and things related to that, you typically, all of your like copy protection mechanisms and things like that, you typically want them to be difficult to reverse engineer so that it takes people longer time to create a crack or bypass for it. So that's one area where you would use this. Or just for any kind of like intellectual property thing where you don't want, like if you're releasing software, but part of the software is actually what you consider, important part of your trade secrets, you can try to obfuscate this code to make it more difficult or take a longer time for competitors to like take your code apart and steal these ideas or algorithms or whatever. Also, malware authors, they use obfuscation heavily to make it difficult to analyze the malware, both automatically, so that you get a lower hit rate from your like antivirus and anti-malware software, but also for like malware analysts to make it more tedious to look at this code. So basically, any time when you don't really want people to know what you're up to for business or other reasons. So, as we know, testing is important when building software. Same goes for when building obfuscators, as you can create some really subtle bugs, and they can be very strange behavior, which can be very difficult to debug. As an example, from this blog post, the Quark Labs people, they found out that if they weren't careful enough, other parts of the like optimization pipeline could choose to optimize away these X and Y variables for some reason, which would cause the program to crash or behave very strangely. So in another article, a guy, he had the actually quite genius idea of just taking some large open source software which already has like a huge test suite and an expected behavior. So just recompile this big piece of software, like the bigger the better, the more tests the better, with your obfuscator, and just run it through all the tests. And if it's still working, then your obfuscation probably did not change the behavior of the program. So that's actually a really neat idea, I think. Instead of trying to like write test cases on your own, just use large batteries of test cases that are already out there. So what do we do about this? And unfortunately, I mean, the answer is basically the same way we handle any kind of obfuscation, with different kinds of reverse engineering methods. So typically when when a tool like this is built by anyone, it's for the purpose to be used on multiple locations. So that means that if we manage to find one sample, let's say a malware author has built an obfuscation obfuscator and obfuscated their malware, and you are analyzing this malware sample, you might be able to eventually, when you've like analyzed and see what's going on, since the obfuscation follows some kind of pattern, you might be able to build an automated deobfuscator for that specific obfuscation technique. And that helps you, of course, if you then encounter another malware which is then packed or obfuscated with the same tool, you are able to reuse your tools against it. So it's like an arms race thing where people will build more horrible obfuscators, and people will try to build then automated deobfuscators. And they can be then specific, as in the example I said, or you can try to use things like symbolic execution, where you try to automatically analyze programs to determine maybe what parts of codes are actually completely useless and optimize them away. One thing I played around with a little bit is that I mentioned this tool called Manticore previously, which is a tool for symbolic execution, and made by the Trail of Bits, US security company. And what you can do is then, if you have a compiled program and you're able to go backwards and turn it back into this LLVM intermediate representation, you can then run these optimizers. For example, the ones already built into LLVM or other optimizer analyzing things to try to remove what is like dead or meaningless code and try to simplify the code again, which hopefully then will remove part of this obfuscation. And then, as always, you can always use your regular like dynamic analysis methods, like debugging and tracing executions, or even fuzzing techniques to see where part of the program behaves differently depending on your input. So yeah, I have some references listed here. I think we'll make the slides available if you want to check out these like blog posts and resources about LLVM and obfuscation, yeah, and these topics. And yeah, that was it. Thank you very much for listening.
All right. Yoo-hoo!
That was great. Do we have any questions, perhaps? We have one from Hugo. Do we have any candy?
No, I'm sorry, we don't. We're running out of candy.
We have beer.
Ah, this guy. This guy. Listening.
Is this not the microphone?
Nope.
You talked about reusing deobfuscation techniques against different types of malware if they've been using the same sort of packer. How often would you say you find samples that have been using the same tools, say in a sample size of 100?
So unfortunately, I don't work too much with, like, in a position where I encounter this on a regular basis. So it would be better to ask this question to someone working, for example, as a malware analyst at an anti-malware company, and they would have a much better understanding of what the landscape looks like. I have more looked at this from like an academic perspective, like as a research thing. So I looked at like specific examples and so, but I have absolutely no idea about like the current landscape of malware, like what the trend is right now.
Anyone else? Don't be shy. Hey, I have no candy. I'm sorry. Nice.
So, in what you have looked at, what would you say would be the performance impact on the obfuscation?
Yes, and that is, there is definitely a performance impact, and of course it depends on the techniques used and so on, ranging from barely noticeable to huge impact. So I think one of the most extreme cases, there is something called the Obfuscator, which I think I've mentioned on this stage previously some year, which basically it's what's called a one instruction VM. So it takes all your machine code, and instead of using this like rich set of feature that your processor provides for you, it translates your code to only use a single CPU instruction over and over again. And this specific case, there are like the multiple examples of these, but this specific case then will only use the move instruction. So if you imagine like a call graph of your program, it will be like a lot of branches and jumps all over the place. When you transform it with the Obfuscator, it all gets turned into one sequential line of instruction that will execute all the time. And that has a horrible performance impact, but it's also absolutely horrible to analyze. So I guess what you could do is you use these like very heavy and performance-heavy obfuscation techniques to like not your whole program, but like parts of your program. If you want to write performant malware or something.
One more? Yep.
I still remember in one of my project, I mean my client project, they used the LLVM to obfuscate their source code. And what I did on that time, I used Valgrind. Valgrind is also one of the tools. And what it will do, it will remove all the obfuscation techniques, date code and everything. And then I perform the side channel analysis on that time.
Yeah, so this is the thing that you have to look out for when you're doing these obfuscation techniques, like because your opponent, the analyst, they have two sets of tools. They have like computers and automated tools, and they have like the human brain. And your techniques, you need to decide for yourself, like what parts am I obfuscating? Like, am I making this difficult for an automated analysis program to understand, or am I making it difficult for a human to understand, or for both of them? And the risk is if you do something that you think like, this is really tricky for a human to understand, but accidentally it's very, very easy for a computer to understand, it might happen that you like just optimize away all your obfuscations on the way, or you make it really easy for the analyst to do this. So you have to consider like what are you protecting against, and how do you achieve that. So.
Sweet. Should we? Anyone else? No.
It's
one more. The final one.
Final question of the day, I think.
There's people sleeping in the back. I don't know why. Just kidding. Here you go.
So you mentioned using Manticore to perform symbolic execution.
Yep.
Another very popular tool that I think you mentioned in the podcast is Anger.
Yep.
Could you give like a dumbed down description of the differences between them, or like?
Yes. So unless I'm completely mistaken, Anger works with its own intermediate representation of the program. So they are not part of like the LLVM ecosystem of tools. So that means that it will only support the things that they have built support for. They cannot like piggyback on this. On the other hand, they're completely free to do whatever they want, and they only have to care about being compatible with themselves. So it's two different frameworks. I actually have more experience with Anger, haven't used Manticore that much, but I think this whole idea, which I think we've seen more and more of the last couple of years, of building things in kind of this like general framework way, is very like fruitful, because like you get these scale benefits. For example, if you look at other like reverse engineering tools, like the Ghidra that was released by the NSA previously this year, they are also doing kind of the same thing. They first they disassemble the machine code into an intermediate representation, and then they run their decompiler on this intermediate representation, which means that they have to build one decompiler for this intermediate representation, and then they have a decompiler that works for all of these different languages or architectures that they are targeting. In contrast then to, for example, the Hexrace decompiler in IDA, which is built specifically for different architectures.
Sweet. All right. Thank you again, Calle. That was great.
Thank you.